Yeah, so hi all, good evening and welcome back to the 7th week of TA live sessions for AI SMPS. Before we get started for today, is my audio clear and is the screen visible?
Yeah, it's clear and visible.
Okay, thanks for confirming. So today we'll be discussing some questions from week 7 of the course, which would be dealing with game playing and several methods to address that, including min max, alpha beta, pruning, and SSS star. Okay, and most of the questions will be revolving around those kind of areas. So without further ado, let's get started. Okay, so this is the first question in front of you. You have been given a pseudocode, okay, that is corresponding to the alpha beta pruning method or the alpha beta algorithm, and each line of this pseudocode has a number associated with it. Okay, what you have to do is you have to point out the line numbers where the alpha cutoff and the beta cutoff occur in this pseudocode. Okay, so it's pretty straightforward question. Please feel free to share your answers in the chat box. Okay, so we have answer in the chat box 6 and 11. That is correct. Lines 6 and 11 are in fact the places where the alpha cutoff and the beta cutoff happen. But can you also pinpoint which of these is the alpha cutoff and which of these is the beta cutoff? Okay, so I've in this figure over here I've pointed out the two lines which have the alpha cutoff and the beta cutoff respectively. So there's a usual confusion that students always have that so the condition for the either of the cutoffs is the same, right? Alpha has to be greater than or equal to beta, but whether it will be a beta cutoff or an alpha cutoff, that depends on what kind of node we are inspecting, right? So if n is a max node, okay, right, if we are inspecting a max node and then we reach a situation where alpha is greater than or equal to beta, that would be a beta cutoff. Okay, and if we are inspecting a min node and then we reach a condition where alpha greater than equals to beta, then that will be an alpha cutoff. Okay, so alpha cutoff happens over here when we are dealing with a min node, right? Whenever this condition is reached where alpha is greater than or equal to beta, we return alpha and we say that this is an alpha cut. And whenever we are inspecting a max node and we reach a situation where alpha is greater than or equal to beta, we return beta and say that it is a beta cut. In any other case, for a max node, we return the alpha value, and similarly for a min node, in any other case where we do not have this alpha greater than equal to beta condition satisfied, we return a beta value. Okay, so this is slightly confusing terminology of the alpha beta algorithm, but I hope that clarifies it for the upcoming applications of this algorithm to different game trees that we are going to have a look at in the live session. Okay, so I'll move on to the next question. It's okay if you are still not comfortable with the whole algorithm given this pseudocode. We'll be going through a proper step-by-step application of the alpha beta algorithm, and hopefully that will clarify any doubts that you have about it. Okay, so moving on to question 2 for now. So here you are given 4 game trees, okay, A, B, C, and D, and these are 2-player game trees, and some edges are highlighted in bold that depict strategies. Okay, which of these game trees depict a game strategy for the root node, which is a max node? So again, make note that for all general purposes, we always assume that the root node is going to be a max node, and there'll be alternate layers of max nodes and min nodes. Okay, and then you have to select each node's children differently depending on whether it is a max node or a min node. So the usually accepted strategy, okay, that we usually follow in such game trees is for a max node we select one of its children, and for a min node we select all of its children. Okay, so with that in mind, which of these game trees do you think would be depicting proper game strategies for the root node? So we have a vote for options B and C. Let's have a look which of these are correct. Just give me a moment. Yeah, I hope you can see the game trees over here. Okay, so the strategy that we just discussed is for a max node we will select one of its children, and for a min node we will select both of its children. So let's go over each of these game trees one by one. So game tree A says that for the first max node, which is the root node, we select the middle child, which is fine. But then for its child, which is a min node, this one that where I'm currently pointing, we should have selected both nodes, this as well as the left the left child as well as the right child, right? But here the strategy depicts selecting only one of them, so this is not a correct strategy. Game tree B says that we select the leftmost child of the root node, which is a max node. Then for the min child, we select both of its children, okay, and then we have the max node layer again, and we select the leftmost child in each case, and then again for the min node we select both of its children. So this is a correct tree. Similarly, game tree C is also correct, which follows similar strategy but just differs in the selection of the min nodes in the third layer, in the fourth layer. Okay, so game tree C is also correct. Game tree D is again wrong because in the first layer itself this depicts selection of all the children of the max node, which is not allowed. So the correct options should be game trees B and C. Okay, so good question, Rajneesh. Why so? So this is a generally accepted strategy that is decided in this domain. We usually go for that, and I suppose that would also have been discussed in the lecture videos. Please do note that this is not something that is 100% applicable in all situations. We are going to see some problems or some domains where we have to change our strategy of selection of the children of each node. For example, SSS start chooses its initial set of nodes that it improves upon following a certain different strategy, but we will discuss that as well. Unless specifically mentioned, we will usually follow this simple strategy where we select one child of the max node and all children of the min node. Okay. For detailed explanations, I would encourage you to go and have a look at the lecture videos. I suppose there you would have a more detailed, in-depth, uh, deep dive into the idea. Okay. Shall we move on to the next question then?
Yeah.
Okay. So now for question 3 to 5, we are going to use a specific game tree. Okay. This is the game tree that is given to you. Okay. The figure shows the game tree with evaluations W corresponding to win, L corresponding to loss, and D corresponding to draw. And this is also drawn from Max's perspective. Okay, Max again indicating that the root node is a max node. Okay, and in this game tree, P, Q, R, and S indicate the strategies or moves at the level of the root. Okay, what we have to do is we have to fill this game tree and decide what is the outcome of this game from Max's perspective again. Okay, and you can assume that a win corresponds to a value of +1, a loss corresponds to a value of -1, and a draw corresponds to a value of 0. With that in mind, I'll let you take some time to fill up this game tree, and then let me know what are the missing values in each of these nodes that are left blank. Okay, so I'll move to the whiteboard where you can see an enlarged version of the game tree, and I'll just, for the sake of mentioning, I'll just write it down here that win corresponds to +1, loss corresponds to -1, and draw corresponds to 0. Okay, so I'll wait a couple of minutes and then we can discuss the solution. So I was muted for a while, Rajneesh. I hope my voice is audible now and the screen is visible. I hope there's no error uh, for others as well.
No. Yes, sir. No issue.
Okay, thanks for confirming. So any partial solutions to this game tree? So remember, as the name suggests, it's a min-max strategy to fill the game tree, right? So a min node will be filled up with the minimum of its children, a max node will be filled up with the maximum of its children. So we have an answer in the chat box that says W is the final outcome, win is the final outcome from Max's perspective. So we'll wait for a couple of more seconds and then we'll discuss the solution. Okay, I think most of you would have already answered it or solved it by now. So let's just quickly do it. So yeah. So let's start with the leftmost position. Okay, so this particular node, all of its children are max nodes and having W value, which is win, which is +1. So this will also be a W. Okay, this max node will also be a W by virtue of this W node, right? This node over here is a min node, so it will select the loss, right? So this will be a L, and this will also be a L because it has only two options, L and L. Okay, and this min node will be a L. Okay, because of three options, win, draw and loss, and it will go for the minimum one, which is a loss. Okay, let's fill in the strategy Q now. So this min node will be filled with either draw or win. Draw is lower than win, so it will fill it with the draw. Yes, was there a question?
No.
Okay. Okay, again, and this max node will be filled up with the max of W, D and L, which will be a W. Okay, this min node will be filled with either W or L. It will go with L because L is lower. This one again will be filled with L, and this max node will go for a draw because that is the max among L, D and L, right? This min node will again go for a draw because that is the least option among W, W and D, lowest option. So we are done with Q. Now let's go for R, the strategy R. This min node is going to have D, and hence this max node will be having a W. This min node will have a W because it doesn't have any other option, and this max node will also have a W. This will also have a W, and now we are only left with one strategy, which is strategy S. Let's fill in that. So this will be filled with a draw because the lower one amongst D and W. This one will be filled with W because of W and W only two choices. This will be again filled with a W because win is the maximum available choice. This min node will be filled with L, this with W, this one with a W again because this is a max node, and this min node will be filled up with a D again because that is the minimum amongst W, D, W and W. Now with all these L, D, W and D strategies that we have come up with in the second layer, the root node from Max's perspective, this will choose the maximum of these outcomes, which is W. So from Max's perspective, we will win the game. Okay, so this is how we fill the game tree. Let's verify that. So win is the outcome when both the players play perfectly. Okay. Any doubts there on how we fill the game tree? Okay, great. If not, then let's move ahead. We have some follow-up questions based on the same game tree that we just solved. Which of the moves P, Q, R and S are best moves for Max? So let me go to the filled in game tree. So out of all these moves P, Q, R and S, which of these moves do you think would Max want to prefer in order to win the game?
R only.
R only, right? Because that's the only strategy that will give it a win. So R would be the answer in this case. Another question.
Sir, what will you do if in case there are two W's, supposing that?
Then it
Then in
can,
that case you have to traverse
in that case, it will follow either of those strategies.
either. So there again we can pick and choose and say that this is the best path, or based on the number of nodes or moves.
Yeah, so this is not exactly a tree that we fill up top to bottom. Okay, this is a tree we fill up bottom to top.
Bottom up.
So
Right.
you can think of it in this way: the first node, the first level of the tree corresponds to the possible move from one player's perspective. So this is from Max's perspective. Okay. The second is from the other player's perspective. So basically, at each level, each of the players have to select one possible move, and
Okay.
as we fill it up from bottom to top, we are going to come up with different strategies that each of these players could follow. Um, the last layer is given to us, so we can use that to fill up the rest of the tree. And let's say two of these, let's say this was not a draw, this was a W.
Hmm.
Then from Max's perspective, he or she would think that okay, both strategies Q and R are giving me a win, so I can play either of these. So he can go by this and then expect the other player to play either of these strategies, W, W, or D, and then somehow or the other it would lead for the Max to win. If on the other hand Max followed this strategy and waited for the second player to follow one of these pathways,
Hmm.
then that would eventually lead for Max to lose.
Okay. So here again, if you see the alternate path, like if we take Q path, you
Hmm.
go from W to D, supposing that,
Hmm.
then it is on the losing side, right? And then W to D, and then D to L, and then from L to L.
W to D, D to no, no.
Then
We don't have to select one of them, right? Like we just discussed. For the max node, we will
hmm,
select one possible child. For the min node, we
okay.
have to select all possible children. That is how we develop the strategy of the game. Okay. Then corresponding to this, it could go for one of them. Uh, let's say this one or this one. This doesn't have any children shown. This for let's say it goes with this one, and then for the min again it has to go with both of them. This complete thing will be called one strategy.
Okay. So if we are asked to, maybe the next question is that only. Yeah,
Hmm.
please proceed. Then
Yeah. So the next question tells us which of the moves P, Q, R, and S will lead to draw if both players play perfectly after the first move. So going back to the tree, so which of these P, Q, R, and S have a draw result after the first move?
Q and S.
Q and S, right? These are the only two strategies that will lead to a draw if both players play perfectly from the Max's perspective. Q and S is the right answer. Right? A way you can think of this is in terms of chess. So I don't know how many of you play chess or are familiar with the rules of chess, but essentially it's a game where if both players play exactly perfectly, the game has to end in a draw. Okay, and for one of the players to win, the other player has to make a mistake at some point. Then that is the only way the one of the players can win, right? But if both the players play perfectly, it has to be a draw. That is an example for chess. Similarly, there might be some other game, for example the game represented in this game tree, where if both the players play perfectly after the first move, then Q and S are the only strategies where it will lead to a draw. If let's say after the first move they follow strategy P, then Max is likely to lose in as per that strategy if Max chooses to follow those set of moves. And if Max goes for R strategy, then it is likely to win. Okay, so tic tac toe is another game that Shiva suggested in the chat box. So that is also something that could be considered. Okay, so this was a simple game tree. We'll be discussing more involved game trees in the coming few questions. But yeah, shall we move on to the next few questions then?
yes.
Okay.
Yes.
Okay, so question 6 onwards, we'll be using the same game tree and we'll be applying different methods to solve it. Okay, the game tree is as follows. it shows a 4-ply game tree. Okay, 4-ply essentially meaning that you can think of it in this way. It's like a look ahead of 4 up to 4 levels deep into the game. Okay, so again we are starting from the max's perspective, then we are waiting for one move, two moves, three moves, and finally till the n plus 1th level the tree is available for us to be able to construct the game tree. Okay, that's why a 4-ply game tree. So an n-ply game tree would have n+1 levels. Okay, 1, 2, 3, 4, and 5. And the leaf nodes, which are at the bottom level, they have the evaluations done, and that is given to us. It is also called the horizon. Okay, the nodes in the horizon carry reference numbers, which are indicated at the bottom here, 1, 2, 3, 4 up till 24. So there are 24 nodes in the horizon, and we have to use this reference number to answer some of the questions whenever required, or to implement our algorithm. And wherever necessary, we have to assume a top down and left to right node order. Okay, another thing about the nomenclature of this game tree that I want to clarify. So we can name these nodes this way. Okay, this you can name as node A1. Okay, A corresponding to the first level or the, okay, this and the second level you can call B, and the nodes you can call B1, B2, and B3. Okay, similarly in the second level these would correspond to C1, C2, C3, C4, C5, and C6. This would be D1 up to, I'm not writing the whole thing, but you get the point, right? D1, D2, and the final layer would be E1, E2 up till E24. Okay, so this is a nomenclature that will kind of help us like make things more uniform as and when we address them during the solution. Okay, now with that in mind, the first question about this game tree tells us to use the min-max algorithm and find the min-max value of the game. Okay, this is similar to the win, loss, and draw tree that we just did, just that here we have real numbers, or not real numbers, integers in place of 3 discrete possible values in the game, right? So here we have different integers, and you have to fill the different nodes based on the min-max strategy. So I'll let you solve it and then we can discuss the solution after a couple of minutes. So Dhruv, to answer your question, it is likely that you would have different questions based on different game trees given to you probably, and different game playing strategies. I don't know if they have reference to any specific game as such, but you can check it out on the assignment webpage. Okay, so I see several answers in the chat box about the final min max value, and yeah, all of you are in fact correct. 68 will be the final value. Let's just have a quick discussion on how we reached there. So following the simple strategy that the min node will be filled with the minimum of its children, a max node will be filled with the maximum of its children. Let's do the analysis. Bottom to top, or
Yes.
let's fill the nodes starting from the second last layer, which is the D layer, because that is the one we have to start filling in. So the minimum of 64 and 80, this will be 64. The minimum of 69 and 68, this will be 68. The maximum of 64 and 68 will be filled with 68. Now coming to this node, the minimum of 90 and 72, this will have 72. The minimum of 16 and 73 will have 16, and this the maximum of 72 and 16 will have a 72 here. The minimum of 68 and 72 will be filled in B1, which will be 68. Okay. Similarly, filling up the other strategies, the minimum of 17 and 84 will have a result in a 17 over here, and 13 over here because of 13 and 42. Here the maximum of 17 and 13 will be 17. Here we will have the minimum of 58 and 92, which will be 58. Here the minimum of 57 and 96, which will be 57. And the maximum of 57 and 58 will be 58 over here. And the minimum of these will be 17 in B2. Now coming to the last one, the minimum of 62 and 78 will be 62 over here. Of 31 and 99 will be 31, and the maximum of these two will be 62 in C5. Here it will have 11, and here it will have 36. The maximum of these will be 36, and the minimum of 36 and 62 will be 36. And based on B1, B2 and B3, the maximum of these will be 68, which is what will be filled up in the root node, which is A1 will have a value of 68. Okay. So this is the min max value of the game, and okay, so I just showed you the answers already, but then you can still find verify your intuition. List the nodes or the node reference numbers that are contributing to the best strategy. And how do we decide that? To decide that, we have to see where this 68 value is coming from. Okay, so let's trace it back. So this 68 is coming from this B1 that has a 68, right? This 68 is coming from comparison of this 68 and this 72. Okay, actually I don't need to draw it as arrows, just lines should be enough.
Sorry, your screen is not sharing, sir, for us.
Sorry, is it visible now?
Yes, sir.
Okay, thanks for pointing that out. So yeah, so this 68 in A1 is coming from this B1, and this 68 in B1 is coming by comparing 68 and 72. Remember, we are choosing to include both C1 and C2 here because we consider both children of min node and one child of max node. Okay, we are following the same strategy again. Now this 68 is coming from this one, right? This 68, and this 72 is coming from this one. This 68 is again coming by comparison of 69 and 68, and this 72 by a comparison of 90 and 72. So 3, 4, 5 and 6, these are the nodes that result in the final min max value of 68. So that's how we deduce it.
So you mean you will have to consider that entire set of leaves together.
Yes.
Starting from that point, you have to. Is it?
Yes. So because all of these contribute towards 68, right?
Selection of that.
Yeah, and we'll keep the strategy in mind that for a min node, both of its children have to be considered. For a max node, one of its children. Here, for example, for C2, let's say we consider only the 70 to the left child of 70 of C2, which is D3 actually. Let me write that down also. So this is D2, this is D3. So we consider only D3 child of C2, and then both E5 and E6 children of D3. Okay, so both all four E3, E4, E5, and E6, all these nodes contribute towards this final 68 in the max. Does that address your query?
Yeah.
Okay, thank you. To answer some questions in the chat box, Dhruv, why not 16 in C2? Because C2 is a max node, it will always select the maximum of its children. And to answer one question in, okay, Lakshmi asks, in Deepak's first slide for one scenario with max leaf nodes with values -1, 0, 0, the parent min node is marked with value 0. Why is it not -1? Okay, max leaf node is -1, 0, 0. Parent min node is value 0. It should be -1. I don't know if that is a typo. Can you raise it up in the discussion forum?
Okay. Yeah.
Okay.
It's in that example which he has been discussing.
I see.
One
I'm
Yeah.
not aware of it. Maybe
Okay.
you can,
Okay.
yeah, just bring it to the notice, and hopefully that will resolve it.
Sure. Thank
Okay. So is min-max strategy clear? Shall we move on to the next algorithm?
Yes, sir.
Okay. Now the intuition behind the next two algorithms that we are going to discuss is our ability to prune some of these subtrees in the game tree. Okay, we don't necessarily want to evaluate each and every of these game trees, right? For example, here we see that the 68 final 68 is coming from this part of the game tree, right? So if we had some way of saying that, hey, I have an intuition that this final value will be coming from this part, and I don't really need to evaluate the second and the third subtrees, this whole part I don't really need to bother about. It would be very computationally efficient, right? Especially in the case when we have huge number of nodes, huge possibility of the moves in a game, like for example chess. It would really make our system efficient. So that is what we kind of do in alpha beta as well as in SSS star progressively. Alpha beta prunes some of these subtrees. SSS star does a more aggressive pruning than alpha beta even. Okay, and we are going to see some of those examples in the upcoming questions. For now, let me erase all of these so that we can solve the other questions. Okay, there we go. So the next question is, simulate the alpha beta algorithm on this game tree, and we have to report what are the number of times we will have alpha cuts and beta cuts throughout the progression of the alpha beta algorithm. And make a note that a single cut, alpha cut or a beta cut, may remove a bunch of edges at once, or in other words, it may remove a whole subtree at once rather than just one edge from the game tree. Okay, so I'll give you some time to try to solve it using the alpha beta algorithm yourself first, and then we will go step by step into the solution. Dhruv, to answer your question, yes, A1 is a max node, so the whole game tree is built from max's perspective. That is the max, that is the min max value of the as per the previous question. Okay, so there's a request to explain the alpha beta algorithm. Let me just quickly go over that so that for any refresher that you might need. So this is the pseudocode, okay? So we have a node n, okay. Each node n has an associated alpha value and a beta value. Let me try to draw it parallelly as well. So let's say this is a node. This could be a min node or a max node. Here I have drawn a circle, but consider it could be any of the nodes. Okay, this is the node n. This has an alpha value and a beta value. Now we initialize all these alpha and beta values starting from the root node with minus infinity and plus infinity. Okay, so alpha value is initialized with minus infinity, and plus value and beta value is initialized with plus infinity, and then we propagate that through all the children of the game tree. For example, if the game tree looked like this, sorry, so on and so forth. I'm not drawing the rest of the game tree, just a sample one. This will have initially a alpha value of minus infinity and a beta value of plus infinity. This it will propagate to all its children as well. So initially this will also have a minus infinity and plus infinity. This will also have a minus infinity and plus infinity alpha and beta values respectively. Okay, each of these are specific to a node though, not common across all nodes. Okay, this minus infinity and plus infinity corresponds to this node alone. This one corresponds to this node alone. Okay, now that we have initialized the alpha and beta values, we have to check for three different sub-modules in the pseudocode. The first one is if n is a terminal node. Terminal meaning it is a horizon node or a node in the last level of this game tree. Okay, it will have a certain evaluation value associated with it. So if n is a terminal node, we simply return the value. For example, if let's say this is the horizon, this is the last level, and this has a value 2. Okay, so this will return the value 2, and because this is the max node, its alpha or beta value will be updated. That we will see in the next two modules of the pseudocode. Okay, we see that if it's a max node, unless a cutoff condition is reached, the alpha value will be updated. Sorry. Yeah, the alpha value will be updated. And if it's a min node, similarly a beta value will be updated unless the cutoff condition is reached. That is the general flow of the alpha beta algorithm. In any situation where we reach when we reach a condition where the alpha value for a given node is greater than or equal to its beta value. For example, let's say for this particular node, let's say instead of minus infinity and plus infinity, we have 100 and 2 or 12, let's say. Here alpha is greater than beta for this particular node, right? So then it will return the beta value, not the alpha value. And oh, this is the min node, so it will return an alpha value, not the usual beta value that it returns, and it will cut off the rest of the subtree associated with it. Okay, so I'll just let this pseudocode be here for a couple of minutes, then I'll shift to the game tree, and then I'll let you try to solve it by yourself first by hand, and then we will go step by step into the solution. Okay, so now I'm moving to the game tree. Okay,
So what is your eval function?
evaluations are just these values given to each of the horizon nodes. For example, here the E1 node has evaluation 64, so that is given to you.
Okay.
Okay. Just to mention one thing about some points in the chat. So I see some discussion about sharing contact information. So I'll just give a gentle reminder that because the session is being recorded and will be shared publicly, please share your contact information only if you are comfortable with sharing it publicly for everyone to view. Okay. In fact, I would advise don't share it publicly over here. You can exchange emails through the discussion forum or some other medium if you really want to collaborate. Okay, let me start discussing the solution step by step, and let me know if you face any doubts at any point. Okay, so as we discussed, we will initialize alpha and beta values with minus infinity. So alpha value will be minus infinity to begin with, and beta value will be plus infinity. This will be propagated to its children. So this will also have the same thing, minus infinity plus infinity. This will also have minus infinity plus infinity. Now this node, this already has evaluation done, right? So it will return a value of 64. Now we have to see whether this will update the alpha and beta value of its parent min node, which is this node. Okay, so this node E1, this will be returning a value of 64 based on the pseudocode that we had a look at. What do you think will be updated, the alpha value or the beta value?
Beta.
Beta value, right? Because this is a min node. and as of now the alpha greater than equal to beta condition has not been reached, right? Because if we update this positive alpha to 64, also 64 is a value lesser than positive infinity, right? So we can straight away say that this beta value will be updated to 64. Now with this updated value minus infinity and 64, we will have a look at what this E2 child has to offer. Okay, E2 child will return value of 80. Okay, now will the beta value corresponding to this min node be updated? Let me again show the pseudocode to you. Remember, beta value is updated only to a minimum of the current beta value and the alpha beta returned by the child. Alpha beta value returned by the child.
64 only.
64 only, right? Because 80 is greater than 64, so this will not be updated. Now that both E1 and E2 children of this min node have returned their values, this will also have a specific value associated with it. Okay, and we can say that this will have a value 64.
Can I ask one question?
Yes.
So what if the condition alpha greater than beta? Are we checking now or
We will
what?
check at every step. Here we still haven't reached a situation where alpha greater than equals to beta, but we will encounter such a situation in the next few steps.
But we have alpha value is minus infinity, beta is 64.
Alpha value is minus infinity, right? So minus
Yeah.
infinity is not greater than 64, right?
Yeah, I agree. But I'm
Uh-huh.
asking, are we need to check at every node or not? That's my question.
At every step we have to check.
Thank you. Thank you.
Yeah. Okay. Now that this min node is filled with value 64, this will return 64 to its parent node, this one. And which value, alpha or beta value, will it get updated?
Alpha.
Alpha value.
Alpha value, right? Also minus infinity is smaller than 64. Oh, sorry. Yeah, I think that makes sense.
Right. You have to arrange minus infinity and 64. Minus into what? Replace this 64.
Now this will be passed on to its next child. Okay, so this will have 64 and infinity.
Infinity.
Now this E3 will return a value of 69. Will it get updated? And what will get updated?
68 will get updated. Beta.
Yes.
Beta. Infinity will update.
Infinity will be updated with 69 first, because E3 is returning 69. Okay, and with this 64, 69, we will have a look at this E4, which is returning 68, which is lesser than 69. So this 69 will get updated to 68. Okay, and this min node will have a value of 68, the beta value. Okay, now this in turn will pass it on to its parent max node, and 68 is greater than 64, so the alpha value will again get updated to 68, and this will have a value of 68. Okay, agree with me till this point?
Yes.
Now this max node will return the 68 value to its parent min node, and its beta value will get updated from plus infinity to 68. Do you agree with me?
Yes.
Now this will pass on minus infinity and 68, minus infinity and 68 here as well, Okay. Now E5 will return 90. 90 is greater than 68. So there will be no change to the beta value. Agreed?
Yes. Yes. Yes.
Okay. Similarly here E6 will also be returning 72, which is greater than 68. So no change to the beta value again. So this will also have 68.
68.
Yeah. By the way, if you have any doubts, please feel free to unmute yourself. Okay. You don't have to raise hands specifically on the Google Meet. Okay. Now
If
that
you can, sorry to interrupt,
uh-huh.
like I had to go through the recording. If you can just explain the logic again from the beginning, if you don't mind, that will help because it has a lot of dependency on the precedence, right? You don't understand the starting point, you won't get the rest of it.
Okay, okay. So okay, let me just quickly start over.
Yeah.
Okay, so we have initialized alpha and beta values as minus infinity and plus infinity, and this is propagated to its child. Each of these has a copy of its own alpha and beta values.
Right.
Okay. Now this E1 node, this has already evaluated and it returns a value of 64 to this min node.
Hmm.
Okay. And because this is a min node, and because the current beta value that it has is greater than the value that this E1 is returning,
Hmm.
this will get replaced by the minimum of those which is 64. Okay, so this
Hmm.
beta value for this min node will change to 64.
Hmm.
Now with this minus infinity and 64 in mind, E2 will return a
Hmm.
value of 80. 80 is greater than 64. So beta
Hmm.
value will not change.
Hmm.
Okay, and then this min node will have a value of 64, which it will return to its parent max node.
Every time we are updating the beta value, right? For every node, we have to update the beta value.
No, it
For
depends on
min
whether
node.
it's a min node or a max node. If it's a min node, we have to update the beta value. If it's a max node, we have to update the alpha value.
Okay.
That is in the general condition. If we have a cutoff, then something else will happen, which we will see in the next couple of steps. Okay. So it will pass 64 to its parent max node, whose alpha value minus infinity is lesser than uh, 64, or 64 is greater than minus infinity. So this minus
Okay.
infinity will get updated to 64. Okay. This 64 and infinity will then be passed on to this one. And with this in mind, E3 will return 69 to this min node. 69 is lesser than plus infinity. So this beta value will get updated to 69. With this 64 and 69 in mind, E4 will return a value of 68. 68 is lesser than 69. So now the beta value will get updated to 68. And this will have a beta value of 68. Now this will return the 68 to its parent max node. 68 is greater than the current alpha value that this max node has. So this will get updated to 68, the alpha value of this max node. Okay, and this will have a value of 68. This will return the 68 value to this min node, whose current beta value is plus infinity greater than 68. So it will get updated to 68. Okay, clear up till this point?
Yes.
Yes.
Okay. Now this minus infinity and 68 will be passed on to its parents. Okay. Now this E5 is returning a value of 90 over here. 90 is greater than 68. So will the beta value be updated?
No.
No, right? It won't be updated. So remember, beta value will be updated only when the beta value being offered is lesser than the current beta value, and alpha value will be updated only when the alpha value being offered is greater than the current alpha value.
Then the beta value.
Alpha will always be compared with alpha, beta will be compared with beta. Okay, here 90 was greater than 68. So we will change, we will not change 68 in that case. Okay. And this minus infinity and 68, with this in mind, E6 will pass on 72 to this min node, which is again greater than 68. So again the beta value won't change. And now that all the children of this min node have been evaluated and the beta value is remaining to be 68, the beta value of, or the returning value of this min node will be updated to 68. Okay, and this will be returned to this max node, whose alpha value is minus infinity, lesser than 68. So it has the alpha value being offered by this min node to this max nodes is greater than the current alpha value that this max node has. So now do you understand whether alpha value will get updated or not? So alpha value will become 68. Are you with me till this point?
Yes.
Yes.
Yes. Yes.
Everyone?
Yes.
Okay. Now, do you see a situation about a cutoff that has been reached?
Yes. Alpha is equals to beta.
Alpha is equal to beta, right? So the condition for cutoff is alpha has to be greater than or equal to beta. Here we have alpha equal to beta. So a cutoff will occur. And by virtue of that cutoff, this whole subtree, sorry, will not be evaluated henceforth. Essentially, we are cutting off this edge, but because we are cutting off this edge, the children of the children below it in the subtree will also not be evaluated going forward, right? So we can just cross it out. Now we have to decide whether this is a beta cutoff or an alpha cutoff.
Beta cutoff.
Yes. To identify that, we have to look at which node we were inspecting. This node that we were inspecting, this was a max node. And let's have a look at the pseudocode. If n is a max node, if alpha is greater than equal to beta, then we return the beta value, not the alpha value. Okay, so usually for a max node, alpha value is returned, but just in the case of a cutoff, beta value will be returned, and this will be called a beta cutoff. Okay, so this will have a value of 68, which is the beta value. Okay, and this part of the subtree will be cut off. This will be passed on to the parent min node. Okay, this already has a beta value of 68 and the beta value being offered is 68, so nothing will change, right? And this will also have a returning value of 68. With me till this point?
Yes.
Yeah.
Okay. Everyone, any doubts?
So far for each and every node we are checking this condition alpha greater than beta, right?
Yes, for each and every node we are checking this condition. For each and every each and every situation where a child is returning a value, in every situation where there is a potential update to either the alpha value or the beta value, we will check the condition whether a cutoff has reached or not.
Okay.
Okay. So now that this min node has a value of 68, this will pass it on to its parent max node. Okay. And this has a current alpha value of minus infinity, which is less than the alpha value being offered, right? So this one's alpha value will be updated to 68. Okay.
Okay.
This will now pass down this 68 and alpha value to its children. Sorry, 68 and infinity. Okay. Now E9 will return a value of 17 to this min node. 17 is less than plus infinity. So beta value will be updated to what?
17.
17. Has a cutoff condition been reached?
Yes, alpha is greater than beta. 68 greater than 17.
Right? Here alpha, which is 68, is greater than beta, which is 17. So a cutoff has been reached. Let me use a different color to mark it. This edge will be cut off and this part of the tree will no longer be considered. Is this a beta cutoff or an alpha cutoff?
Alpha cutoff.
Alpha cutoff, right?
Alpha cutoff.
Because the node being considered was a min node, and again if you have a look at the pseudocode, for a min node, if alpha greater than equal to beta, then return alpha, so it is an alpha cut, otherwise return beta for a min node. Okay, so this is an alpha cutoff and this was a beta cutoff. Okay, now let's proceed with the rest of the algorithm. So this returned the alpha value, right? So this got a value of 68 and this will now pass on 68 to this one, this max node. This already has a alpha value of 68. So will any update happen?
No.
No updates, right? The alpha beta value will remain as it is. This will now be passed on to this child, 68 and plus infinity. And again this E11 will return a value of 13. Will any updates happen in this case?
Yes, beta update 13.
Beta 13.
Exactly. So this beta value will be updated to 13. Again, has a cutoff been reached?
Yes.
Right? Alpha is greater than beta. So we will have one more alpha cutoff and this part of the subtree will be cut off. This is also an alpha cutoff and this will return the alpha value, which is 68. Okay, so this will again return 68. The alpha value will remain 68, so no change. This will have a value of 68.
No. So again, hello.
Yeah,
I hope that is here we have to write 13, right? Because that is minimum beta.
no. So this will return a value of alpha, right? Because the cutoff is cutoff is happening. So for a min node, when a cutoff happens, we return the alpha value.
Okay.
Okay,
Got it.
here when the cutoff happened, the alpha value was 68. So we return 68. Okay.
Good.
So this will have a value of returning value of 68. The 68 will now be passed on to its min parent, whose current beta value is plus infinity. Will it be updated?
Yes. 68.
Yes, it will become 68 and again a cutoff condition has been reached.
Yes.
So in this case, what kind of cutoff will it be?
Beta again.
Sorry?
Alpha
Oh,
cutoff.
okay. Alpha, 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 minimum, minimum alpha.
Yes, it will be an alpha cutoff, right? Because it's a min node. So
Yeah.
this edge will be cut off, and by virtue of cutting off this whole subtree will be cut off as well. This will also be an alpha cutoff, and this will return the alpha value, which was 68. Okay, this will now pass on 68 to this max node. This already had an alpha value of 68, so no change will happen. This will now pass on this 68 infinity from here to this part. Okay, here something similar will happen to what we just discussed in the second strategy, okay, which is this part. A very similar situation will occur. Here E17 will return 62, which will update the beta to 62. Again a cutoff condition is reached, right? Alpha is greater than beta, 68 greater than 62. What kind of cutoff is this again?
Alpha cutoff.
Correct. So this will also be an alpha cutoff. And this will have a value of how much?
The alpha value 68.
68. Okay, this again will be passed on over here. No change in alpha value, right? Because 68 is already there. Now this will again be passed on to this fellow, 68 and infinity. E19 will return 31, which will update the beta value to 31. Will there be a cutoff again?
Yes.
Alpha
Again,
cutoff.
alpha.
Again an alpha cutoff will happen. This part will be removed, and
68.
68 will be the returning value, correct? This will return 68. Again no change will happen to this node's alpha and beta value, and this will have a returning value of 68, correct? This
Yes,
will
yes.
return 68 to this min node, which will again result in the beta getting updated to
68.
68. Again a cutoff.
Yes. Again,
What?
alpha.
Again alpha, correct. This will be cut off, and the whole subtree will also be cut off. This is one more alpha, and this will also return 68. This will also return 68 to its parent max node, which already has an alpha value of 68, so no change will happen. And finally, this max node will return a value of alpha value of 68, and we have concluded the algorithm. So how many alpha cutoffs and how many beta cutoffs did we encounter?
6 alpha and 1 beta.
6 alpha
6 alpha and 1 beta.
and 1 beta. Let's verify that answer. Six alpha cuts, 1 beta cut. So we solved it correctly. Now I'll leave the solution here for just a couple of minutes so that you can convince yourselves in case there is any confusion before we move on to the next question.
Can I ask one question?
Yeah, sure.
Actually, this advisor search follows DFS algorithm, right?
Sorry.
I mean, that means it follows queue, data structure queue. No, stack, DFS.
So I think it's better to think of it in, I mean, intuitively it's better to think of it this way, that whenever you have to evaluate, you keep evaluating it left to right. So when you start with this let me use this other marker. This over here, you first pass it on to this leftmost child, which is passes on to the
Yes.
leftmost child, which passes on to the
Yes.
leftmost child, which
Yes.
gets the returning value from here. And then
Yes.
this gets updated, then it goes over here, then here, so on and so forth. So yeah, in a way it is similar to DFS, but just to not confuse it with other search algorithms, let's just, I mean,
Okay.
if it
Okay. Got
works
it.
for
Got
you,
it.
yeah, if it works for
This
you,
is
you can call it. But yeah,
okay. Got this is not
Uh,
such a. This is yes.
Sir,
Right. Got it.
just a minute.
yeah.
What is the application of this alpha beta algorithm, sir?
So this is used for game playing strategy, coming up with a game playing strategy, right? So for example, min max was one strategy we used to come up with the final outcome for a particular game given a game tree. Correct, in the previous question. Do you remember that?
Correct. Hmm.
There we had to evaluate all the nodes in the whole game tree given to us.
Correct.
Alpha beta gives us a more efficient way to kind of prune off certain subtrees like you saw over here using alpha and beta cutoffs, so that we don't have to evaluate each and every of the node in the game tree and still arrive at an estimate of the final outcome of the game following certain strategies. So here we know that the final outcome will be 68, and that 68 will eventually probably come from this left part of the game tree, because that is the part where uh, yeah, the 68 is basically originally coming out from this e4, right?
But the competition time will be more here, na, compared to
Computational
that
will
min
be
max.
less here, right? Because once you are doing the cutoffs, this the subtree that is getting cut off, you don't have to worry about updating the alpha beta values of them or solving the returning value for each of the nodes in that subtree.
That's okay, but iterative way of thinking is there, na, here. Iterative way of doing the work. So it will
That
be more, I think so.
that will be there in min-max as well, right? In min-max, you have to go through each and every node iteratively and then evaluate it. Here, while evaluating, you are looking at, for example, let's say this point. Okay, at this point, when you evaluated this particular, when you reached this condition, you saw that okay, here cutoff has been reached. So instead of evaluating this as well, you just ignored this and moved straight ahead to this one.
Mm,
Correct? Similarly,
correct.
here, when a cutoff condition was reached, you just ignored this whole part. You didn't care what value will come here, here, here. You just move straight ahead to this part. That is the advantage that alpha beta offers.
That the time complexity will decrease.
Yes.
Okay, thank you.
Yeah. Sure. So Ashwini, to answer your question, this is in fact a small game tree. Usually, if you have some more complicated games like chess, for example, the game tree will explode exponentially. So there we won't be able to map it out by hand. You can come up with an even smaller game tree and just run the toy example using alpha beta. Okay, like we discussed, and hopefully that will help you resolve some of the questions, some of the doubts that you have. Okay, so I'll just wait for a minute, then we can move on to the other method that is left for today. So I hope the remaining questions in the chat box by Varisha, Baswaraj, Nandana, I hope your queries were addressed while we solved the whole alpha beta algorithm. If not, please let me know. Okay, shall we move on to the next question then?
Yes.
Okay. One more thing that I wanted to point out to you. There is this very nice trace that has been developed by Bhaskaran sir. Okay, and that is available in the same folder that contains the slides for each session. Okay, and you can visit this as well, or go through this as well to go look into a step by step, more in implementation friendly version of the solution. Okay, we solved it by hand manually. This is more like if you had a code written, what are the steps that you would have followed. Okay, so just wanted to point this out to you. Okay, and you can have a look at this again whenever you want to revise the method. Okay, the next question asks us, what are the total number of strategies in game tree 1? So what do you think is the total number of strategies? Remember the rule that we were following initially: one child of max node, all children of min node. Okay, so we have a couple of solutions. Let's have a look. So let's mark color code each of the strategies. Okay, so one strategy could be we chose this particular child of the first max node, then both of these, then let's say leftmost of this, and then both of these. Okay, one more strategy could be that here it's still the same, but instead of choosing the leftmost, we chose the rightmost. This would still remain the same. Or it could be that you chose this, this one, and this one. So the essential choice that you have to make is lying at this level. If you notice, at this particular level, right? How many different edges are there in this level? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So essentially you will be left with 12 strategies. Okay, and that is the total number of strategies in the game tree. Okay, shall we move on to the next question
So,
then?
what if there are two more levels?
Then the horizon will be at a deeper level, and then the number of strategies will be decided by the penultimate layer over there.
Okay,
Yeah,
thank you.
okay. Okay. Now the last algorithm that we are going to have a look at is the SSS star algorithm, and like we discussed previously, this does even more aggressive pruning than alpha beta. Okay. So what this does is this starts with some initial number of clusters that it requires for the algorithm. Okay. And how it decides those initial clusters is different from the usual rule that we use to come up with or identify strategies in the game tree. So usually what we do is one child for max node, all children for min node. Correct? Do you agree with me?
Yeah.
Here what
Yes.
we will do is all child for max node, all children for max node, only one child for min node, and that also we will fix to be the leftmost child of the min node. So if we mark that over here, let me erase all of these. So we select all children of the max nodes. Okay, so this, and this, the leftmost child of the min node. Again, all children of the max node. Leftmost child of the min node. So E1, E3, E9, E11, E17 and E19. These will form the initial clusters that will be used by the SSS star algorithm. This is where the strategy is different from the usual strategy we follow. Okay, and please remember this when you solve the algorithms, because this can be a bit confusing. Okay, so Dhruv, to answer your question, you're asking what exactly is the strategy, right? Let me draw that for you. Let's say we chose to go this one, this, this and this. This whole selection of moves at each level, this one at the first level, these two at the next level, these at the next level, and these four at the final level, this whole thing constitutes one strategy. Okay.
Okay, sir.
Okay. Rajni, in question 8, we just came up with how many different strategies could be there in a game tree. So like we discussed one strategy over here that I just showed to Dhruv. You just have to check how many different such strategies could be there in the game tree. Okay, and that is essentially decided by the penultimate layer, right? And here we have 12 such edges, 12 such combinations of 12 strategies. Okay, now that we have understood how we come up with the initial clusters for the SSS star algorithm, let's get into the algorithm itself. How SSS star functions is by using a priority queue. Okay, let me erase this first. And in order to depict that priority queue, I will write a representation over here. So we will start with the root node, which we called A1. Okay, we will say what type of node it is. It's a max node. What is the status of the node? A live node. Okay, so any node that currently doesn't have a value associated with it is a live node. Okay, and any node that has a value associated with it are solved nodes. So here only the horizon nodes are the solved nodes. Okay, so this status is live, its bound is infinity. Okay, it can take a maximum of infinity, and then the current value we will leave blank. This is what we are starting with. Okay, now what we will do is we will add the children of this max node. So this was A1, this was B1, B2, B3. We had to add all children of the max node to the priority queue. So let's add that. And while doing that, we will pop out A1. Okay, so we will pop out A1 and we will add B1, B2, and B3 to the priority queue. B1 will be a min node, it will also be live, its bound will also be infinity, and its current value will be left blank, but this is because it's currently not solved. Okay, now for B1 we will add the leftmost child of the min node, which happens to be C1. Okay, so we will pop B1 and instead we will add C1, which is a max node, live node, bound infinity, and again unsolved, so we will leave it at that. Okay, now C1 is a max node and all its children, which is D1, and D2 will be added to the priority queue. Okay, so C1 will get popped out and D1, which is a min node, will be added, and D2, which is a min node, will be added. Okay, so this is what the queue will look like at this point. Now D1 is at the top, and D1 is a min node, so the leftmost child of D1, which is E1, will be selected, right? So D1 will be popped out and E1 will be added. E1 is a max node, it is currently live, but it will get solved just now. Okay, its bound is infinity, current value is unknown, but we know that E1 returns a value of 64, so we can say that this has a value of 64. Okay, now we can label it solved. And once it is solved, we will move it to the back of the end of the queue. Okay, now the next node at the top is D2. What is the next child of D2? The leftmost child of D2 is E3. Okay, so E3, D2 will get popped and E3 will be added. E3, which is a max node, currently live, bound is infinity, value unknown. We know E3 returns a value of 69, so let's add that. We call it solved, and it will be pushed to the end of the queue. But remember, this is a priority queue, so can anyone tell me whether E3 will be placed before or after E1?
It should be before
before.
E1.
Correct. Because it is a priority queue,
Thank you. Hmm.
so its position will be decided by its value that it is returning. Okay, and because it is greater than 64, this will be placed above it. Okay, now the next thing at the top is B2. Now when B2 will be popped, the leftmost child will be added, right, which is, sorry, this will be C3. Correct. So B2 will be popped, C3 will be sorry, C3 will be added, which is a max node, currently live, bound infinity, and value unsolved. Okay, this is what the priority queue looks like. Next, C3 will be popped, and what will be added? Can anyone tell me?
D5.
Yes, D5, just D5?
D5, D6.
Yes, both children of a max node, right? So both D5 and D6 will be added. So D5 as well as D6. Next, D5 is at the top. So D5 will be popped, and what will be added? Let me number it for you.
D9.
Yes.
E9.
E9, the leftmost child of D5. E9.
Student బాగా ఎక్స్ప్లెయిన్
Uh, can you please mute yourself if you don't have a question?
చేస్తామా
Okay, maybe I'm muting
70.
you. Oh, I suppose you were saying something. Sorry about that. You can unmute yourself, please, again. Yes, so now this will return a value of 17, and this will be called 17, and this will be labeled solved. And where will this be placed?
Before E3.
Before E3, are you sure? Because see, it's
No,
a
after
priority.
E1.
Yeah, this value is lesser than E3 as well as E1, right? So they should come afterwards.
Okay.
Okay. Okay. Now D6 is at the top. So when D6 will be popped, what will be added?
E11.
E11. E11, which is a max node, live and infinity, bound, current value not known. It will return a value of 13. So
So
13.
E12 also.
Sorry.
Oh, sorry. Minimum.
E12 also will be there. 11 as well as 12 both will be there. No?
No. Leftmost child of the min node, right?
Minimum. Maximum only two sides.
Yeah. So only E11 will be returned.
Actually, this is a bit confusing.
Yeah, I understand.
Do we have the algorithm written down somewhere so that can follow?
Yes, I suppose the algorithm will be there in the lecture slides, right? If not, at least in the lecture material, it should be there.
It's there in the lecture material.
Okay.
Yeah, it should be there. Okay, so have you placed E11 in the correct position?
Yes.
Okay. Now B3 is at the top. Do you already see what are we doing here? So this E3, E1, E9, E11 were they part of the initial clusters that SSS star we said that SSS star will be using?
is mentioned.
Right. So essentially, what we are doing here is implementation wise coming up with the initial clusters. Okay. Okay. So now B3 is at the top. For B3, what will be added?
C5.
Correct. This was C5. This was C4. This will be D9 and D10. Okay. So when B3 gets popped out, C5 is added. C5 is a max node, live, infinity bound, and current value unknown. Now once C5 is popped, what will be added?
D9, D10, both.
D9 and D10 both. Correct.
D9.
D9, which is a min node, and D10, which is also a min node. Now when D9 gets popped, what will be added?
70.
E17. That's correct. E17, which is a max node, live and infinity bound, value unknown. E17 will return a value of 62.
Yes. In between E3 and E1.
Yes, that is correct. Over here, right? Next, D10 will be popped, and what will be added?
E19.
E19. That's correct. E19, which is a max node, live and infinity bound, and current value unknown. E19 will return a value of 31. This will be labeled as solved. And where will this be added?
Before E9.
That's correct. So now these are exactly the initial clusters that we came up with. Do you agree with me?
Yes, sir.
Right. Now that we have the initial clusters, we will follow this strategy. So E3 is at the top of the priority queue currently. Okay. So what we will do is we will add the immediate neighbor of E3 to the priority queue as well. What is the immediate neighbor of, or not really a neighbor, but an immediate
E4.
sibling? Yes. E4 is the immediate sibling of E3. So we will add E4. E3 will be removed. E4, which is a max node, live. Now the bound will change. Okay, bound will no longer be infinity. It will be decided by the value of the sibling node, which is E3. Okay, so E3 had a value of 69. So this will become the bound for E4. What is the value that E4 is returning? E4 is returning 68.
68.
68. Okay. So this is how the queue will look like. We will next label E4 also as salt. Okay. and we will change the bound. This will become 68 too. Okay, so this is what the parity queue will look like after one operation of including the immediate sibling of the topmost node in the parity queue. Now E4 doesn't have any other sibling, right?
Yes.
So now both the children of D2 have been solved. Agreed? Both E3
Yeah.
and E4 have solved status. So we will.
Can you come again from E4?
So E4 doesn't have any other sibling, right? So no scope of
Yes.
further expansion. And both the children of D2 are now solved. E3 is also labeled solved. E4 is also labeled solved. Agreed?
Oh.
So
Before
we
we
can.
have 16, right?
Sorry?
Just one step before we have 16 and 68. How come we got 68? How come we got 68?
Yeah, so initially the bound was decided by E3, right?
Yes.
Now that we have solved E4 and 68 is less than 69, we update the bound to 68, the current value.
Because D2 is minimum.
Yes, I mean,
Okay.
yeah, you can think of it that way, but this is more like a. Yeah, I mean, yeah, that is how you will proceed.
Okay.
Sir, I have a doubt.
Yeah.
There is a tiebreaker. There is a question regarding this in the practice assignment.
Okay.
They have given a tiebreaker when several nodes have the same H value, then select the deepest leftmost node.
Okay.
What is
Tie in case of what?
there is a question like what are the horizon nodes that are assigned solved status by triple S star algorithm?
Okay.
And then below that they have given one note tiebreaker when several nodes have the same H value, then select the deepest leftmost node.
That might mean that if in some situation in the priority queue you have multiple nodes that have the same value that they are returning, you have to select the deepest leftmost node, which means that in this order the deepest node will be at the horizon, correct? And the leftmost node will be the one that is in the leftmost part of the horizon. That is the one that will be popped next. I suppose that is what they mean. That seems to be the logical explanation to me. Uh, but why don't you also get that verified from the discussion forum? Okay. Okay, now that both E3 and E4 are solved, we can say D2 is also solved. Okay, so D2, which is a min node, is now solved. This has bound 68. Sorry. And the value being returned is also 68, you can write. Okay. Now there is a rule which says that whenever one min child of a max node is solved, just give me a moment. Yeah, so whenever one min child of a max node is solved, we can straight away say that that max node parent is also solved. Because here D2 is labeled as solved now by us, we can say that C1 is also solved. Are you following me?
Yes, sir.
Okay. So we will remove D2
And C.
we will add C1, which is a max node, which is solved, bound of 68, also returning 68. And because C1 is also solved, we don't really need E1, right? Because C1 is solved through D2. So E1 will be also pruned out. We don't need E1 anymore in the queue. Okay? Are you with?
Sir, even is solved or even is pruned?
E1 is solved eventually. E1 already had a solved status, right?
Yeah.
But now that C1 is solved, we don't really need to debug E1 again.
But E2
Okay.
is also solved here.
E2 is not solved.
Not solved. Because C1 is solved, right?
E1
All
is
the
solved.
horizon, all the horizon nodes which come under C1, that also is solved, right?
I mean, yeah. So so yeah. So actually, let me correct myself. E1 is solved. E2 is also
No.
solved. Um,
Okay.
D1 we don't need to solve. Okay,
That's what,
because
sir. D1 we don't need to solve. It is understood that E2 is also solved.
yes, all horizon nodes are solved because they already have the values assigned to them.
Okay.
Okay. So now this is the situation in front of us. Now C1 is at the top of the queue. Okay. What is the immediate sibling of C1?
C2.
C2.
C2, right? So C1 will be popped, C2 will be added, which is a max node. It is currently live.
Alpha. Yes.
Bound will again be 68. Current value, let's leave unsolved at the moment.
The 68 carry forward from C1 to C2.
Sorry?
The 68 value is carried from C1 to C2.
Yes, exactly. Okay. Now C2 is at the top of the priority queue. And we will apply the SSS star algorithm recursively now. So this is C2, right? This is C2, this is D3, this is D4. Consider this as an independent subtree and apply SSS star again to this subtree alone. Okay, that is what essentially we are going to do. C2 will be popped and what will be added?
D1 and D2. D1, D3, D4.
D3, D4, right? So C2 will be popped. D3, which is a min node, live, bound is 68, currently unsolved, and D4, which is a min node, live again, bound 68, also unsolved. Next, D3 will be popped, and what will be added?
E5.
E5 will be added. E5, max node, currently live, bound is 68, value unknown.
But it will be solved.
Yes, it will return a value of 90. It will be labeled solved, and because the bound is 68, the value that it will return will also be 68. Okay, so this is what it will look like.
So for suppose if you got 67, then the bound value changes, right?
Yes, then the bound will change. Next, what we will do is so we are at E5 currently, right? E5 will now be popped, and what is the immediate neighbor of E5?
E6.
E6.
E6. So let's add E6, which is a max node, which is live currently, bound is 68, this is unknown. This will return a value of 72, label it solved, correct?
Yes.
Now both E5 and E6 are solved.
Bound becomes 72. Is it bound becomes 72?
No, it has to be lesser, right?
Okay, sir. Okay, sir.
Yeah. So can we say that D3 is now solved?
Yes.
So D3, which is a min node, is now solved. Bound 68, value 68.
So once D3 solved, we no need to bother about D4, right?
Yes, we don't need to bother about D4. We can say C2 is solved.
Okay. So
And
we
we can
can remove
also,
D2,
yeah, we can
D4.
also remove D4 because we don't need that anymore.
Okay. And C2
So we will say C2, which
max
is a max node, is
solved
solved, bound
68.
68, value 68. Okay. Now both C1 and C2 are solved.
Yes.
Can we say B1 is now solved?
Yes.
Yes. So let's replace C2 with B1, which
So
is,
we have to take in between the maximum value because
I mean, here both are returning the same value.
we
And
suppose.
so B1 is a min node. So you should
Okay. Okay.
take the minimum, right?
Okay. Okay. Fine.
So B1, initially B1 will be, okay, B1 will actually be solved
Solved. 8,
and 68, 68.
so
Okay.
my but B2.
So B1 is solved. One min node of the max node A1 is solved. Do we need to bother about B2 and B3 anymore?
No need.
No, sir.
Exactly. We don't need to bother about B1, B2 and B3 at all. We prune everything that is remaining. We add A1, which is a max node,
It's solved
solved 68,
68.
68. And essentially what we did is, sorry about that.
Yeah, B1 is a min node, right?
B1 min node, right?
B1 is a min node,
It's
yes.
not max.
Yes. We have pruned out this whole portion of the game tree. This whole thing, this whole D4 thing, we said that we don't need to, I mean, we didn't really prune it. I mean, yeah, we pruned it technically, but we just said that we don't need to solve it anymore. D1 also we said we don't need to solve anymore. So with just these many evaluations,
Still we got the same answer.
and D3, we got 68. So this is SSS star algorithm. I know it's quite a bit complicated in the first go. So again, the traces for this are also provided to you in the same folder. Okay, again, this has been prepared by Bhaskaran sir, very beautifully prepared.
Thank you very much.
So please make use of this. Okay, go through each step one by one and solve it by your own hands. Okay, and that will give you an idea of how to attempt it in case of other game trees given to you. Okay, so make use of this. I suppose there are also some other examples provided in the practice assignment, so also solve those.
Excuse me, sir.
Yeah, just a minute, let me just complete this question. So the question told us what is the number of initial clusters found by SSS star. We just saw that there were 6 of them, right? E1, what were they? E1,
E3,
E1, E3, E9, E11, E17 and E19.
13.
Yeah. So those were that was the question. And what are the horizon or other assigned solve status by SSS star once the algorithm completes? You can verify that yourself based on the algorithm that we just discussed.
Come again, what is the question?
What are the horizon nodes that have been labeled solved when the algorithm terminates?
Okay.
I think this is what you were also referring to, right? One of you were asking this, right?
Yes, sir. Yes, sir.
Yeah, I hope that clarifies it. So yeah, there was a question, right?
Hello.
Yeah.
So in the practice session, if we follow the same method,
Hmm.
some of the like what answer we get at the end, the solved notes and pruned notes,
Uh-huh.
that won't match with the answers given in the practice assignment.
Can you please bring it to the notice of the NPTEL team? I think this
Yeah.
also happened in the last week where
Yeah.
where the solution of
Yeah.
the SMGS problem was not matching.
Yes, yes, yes.
I have also conveyed it.
Two practice assignment is given, so two different problems are there.
Uh-huh.
In one practice assignment, the answer is different, and if you follow this method, it is not matching with the answers what is given there.
Okay, so based on my understanding, I think what we discussed today is supposed to be the
Yeah,
logical
yeah, I
approach.
have watched your previous 2 3 years video also on lecture 7. The
Mm-hmm.
same answer is there, but in the practice assignment answers, if we give, no, it is not. So
Okay,
that is why we have a confusion in the final assignment answer, week 7 answer.
I understand. I highly encourage that you, as soon as possible, bring it to the notice of the NPTEL team and get it resolved.
Yes.
Um, for the last week at least, from my side I conveyed it to the team, and I don't know if they've made any changes or not. I didn't check, but please check the
Okay.
SMGS thing as well, and this as well. Okay, because I suppose there's only one day left for the assignment
No.
deadline.
Yes, sir.
It's better if you get it resolved as soon as possible.
Okay, sir.
Thanks for the last estimate, but I lost the marks.
Oh, is it?
Yes, I only raised the point SMG. If you
That's
remember,
yeah. I remember.
yeah.
I mean that, as per my understanding, we followed a logical procedure. I don't know why there is a
Yes, yes.
discrepancy. Um,
No one would have to follow you. Better to skip the practice if any deviation. That's
uh,
what I learned in the last assignment.
no, I would still suggest that you do solve the practice assignment, and if there is any discrepancy, please get it clarified by the discussion forum. There might be some errors that maybe I am committing, or that has been committed by the from the end of the NPTEL team who has provided the practice assignment answers. In either case, it's better to get it rectified as soon as possible so that whoever is wrong, be it me or the NPTEL team, they can correct it going forward in the future.
But Bhaskar sir given only algorithm reply. For me, it's only algorithm again.
Oh, he
So I don't
replied.
know what to. He replied me, but he given algorithm. Check my algorithm once again. That's it.
Can you provide your solution also to him? Um,
Not solution, but I given the screenshots of practice assignment and
hmm,
my answer. So then I said there is a deviation.
I see. Can you
Is
also,
is
or not necessarily you, but any of you who might have solved it, can you also give a, like a step by step worked out solution so that he can verify it uh, and
So is
see?
it in can we mail our solution
Yeah,
in the
yeah.
forum?
So there is this discussion forum, right?
Yes.
Where you can essentially mail your
Okay.
solutions to a group. It's a Google group,
Okay.
and
Yes, sir.
I really hope it gets addressed um, and it gets clarified in time. It's really unfortunate if some of you lose marks because of a simple
Yes, sir.
confusion, and I hope from my side I have done what I could. I hope I
yes.
am not wrong. If I am wrong, please forgive me. But I feel that
No, no,
we
no. The
discussed.
last one you're right, but I followed the practice assignment, but I lose the marks.
Yeah, let's hope. Fingers crossed,
In
and
practice
let's.
assignment 1, we have a different answer. The same thing is not applied for practice assignment 2.
Oh,
Week 7 practice assignment 1 and week 7 practice assignment 2. Two different problems are there. If we apply this in one case, it is not. In other case, it is like that. That is why we are not clear. We have that doubt. Which one
yeah.
to follow?
I think it's better to get it clarified by the people who have set that question. Okay.
Okay.
Okay, that's it from my side from today. And I think we have
So I
also.
have a doubt in assignment questions. Week 7, 15th question, they have asked the e value to be changed. How can we solve that, sir?
Which question is it?
Week 7 assignment 15th question, sir, 15 and 16.
So it just says that the current value that this uh, change the eval of exactly one horizon node to get a min max value of 46. So what essentially says that you have to choose one of these min nodes, one of these horizon nodes, sorry, not min node, horizon nodes, and replace the current value with the given value, so that the final value that you reach in the that you get in the root node is 46, and you have to try that out. Okay, I can't help you much with that.
Okay, sir. Sir, I
Unfortunately.
can change any value, or particularly I should change the final value, that max value.
Have a look at the question. What does the question say? Change the eval of exactly one horizon node to get a new min max value of 46. Which node will you change and what will be its new eval? That is exactly what you have to answer. So you have to choose the smallest integer value possible for the horizon node that you wish to change. If multiple horizon nodes qualify, then pick a node of your choice. So you have been given hints, right? So just follow that.
Okay, sir. Thank you.
Okay.
Yes, sir.
Okay. Anything else? So Dhruv, to address your query, yes, lecture material should contain extra notes by Bhaskaran sir. Please go through that as well. Okay. So take your time with these methods. These are a bit involved in the first go, but as you practice, you will get a hang of it.
So
Yeah.
we have some more example problem statements related to the kernel node and then the boundary one. Solved problems for reference.
Yes,
Uh,
please. My side of the same request.
so what we
Because we
can do
have
is
very limited problem set, and last time what happened, your recording, yes, we are listening to it, but it is made available the same day night. So in your recording, and if you have to listen to, there is no other reference.
I understand. Maybe what you can do is search if there are other tutorials that have also done something similar, and if they have other smaller, more easy to understand, simpler graphs that you could address using SMGS or something like that. From my side, what I can do is there might be a possibility that we will have an extra session after all the 12 weeks. Okay, that is the
Okay.
13th live session. I can
Hmm.
try to incorporate some extra questions based on these difficult topics, relatively difficult topics in that extra live session. That's what I can do from my side. But other than that, um, yeah, I don't know what else should be done.
Because last week assignment was the toughest one as far as my understanding goes, and even the marks are also low. So, uh,
Yeah, I
because
get
many complex problems we have to solve, and
I get
I
you.
think
Yeah, I get your point of view. But then, see, I also have to. So, all these questions that I am discussing currently have either been designed by Bhaskaran sir or
hmm,
are from previous iterations of the course. There are
hmm,
few questions that I have designed myself,
hmm,
um, because honestly, designing questions is a difficult task, right? And it takes quite a lot of
Yes.
time.
Yes.
And I can try to do that for the last live session, but it'll take me some time. And the immediate solution that I can see is maybe other tutorials that could have extra problem statements and solutions that could be referred to, or the practice assignment um, um, that are given in the Swayam portal. One more thing that could be done is, because we are talking about artificial intelligence, use large language models. Okay, take ChatGPT or Gemini or anything, ask them to give
hmm,
you a graph, and then ask it to
hmm,
solve it using SMGS. Give it the whole algorithm, ask it to
hmm,
solve it. There are high chances that LLM will make a mistake, not one mistake, multiple mistakes. You have to
Yes.
verify
Yes.
that
They
yourself.
do. They
hmm,
do. I
Yeah,
did the exercise. They do the mistakes.
yeah. But then that will also be kind of a nice exercise for you. You will get to be the evaluation evaluator as well as the student. Okay, so that is one way to address it as well.
I did that same exercise, but even though there is no proper conclusion after using ChatGPT also.
Yeah, yeah. They are likely to hallucinate, right? So they will make errors.
Even I'm teaching ChatGPT how to solve SMPS.
I see. Yeah, that's a nice solution.
Maybe next session, if you can just give us one simple and solve problem on boundary and kernel node,
I can
just half of it, that will help us a lot.
I
That's
can
a
try,
request.
but I can't guarantee. Okay, because
Okay. Okay.
usually what I do is I use these established questions that I've been
Mhm.
using,
Mhm.
and the rest of my week is kind of packed with other things that I have to do. So it's really difficult to take out time for designing questions. I will try, but I can't give my word. Okay.
Okay, as you said, after 12 assignments, we can see.
Yeah, there I will try to incorporate some more questions because I will have relatively more time to think about extra questions.
Okay.
Okay. Also, that also depends on whether NPTL will let me have an extra session. Okay, so there are a lot of ifs and buts.
So
Let's see.
we will request everyone in the discussion from
So
acceleration.
usually they offer us themselves. Let's just wait and see. Okay.
Okay.
Yeah. Okay. We can conclude the session for today. I really have to run somewhere. Thanks all for attending, and hopefully this was of some help.
Thank you, sir.
Request to upload this video at the earliest.
Yeah, I'll try to upload it by tonight itself.
Yeah, thank you.
Thank you.
Okay. Thank you.
Thank you. Thanks for your patience.
Thank you.